Hello everyone. Now we are going to see about common gate stage. So first of all we will see what is common gate. So in this common gate stage we are going to discuss what is common gate stage and what is the gain and what about this input and output impedance, and next behavior of common gate stage with finite source impedance and biasing, that is common gate stage with biasing. These are all the things we are going to see now. First of all, we'll see what is the common gate stage. We already know this is what my CMOS transistor. So here I am having, this is my gate, this is source, this is drain. So common gate means gate is common to both drain and source, both input and output. So this is common. This will be connected to constant supply, otherwise ground. That is AC ground. Otherwise we can call it as constant DC voltage. And this is my source. So where I am giving input, we have to give the input at source side, and we can take the output at drain side. So input should be given to source side, output can be taken at drain side. This is what the common gate stage diagram. Here, if I am increasing my input by a small amount, let us take that is del V. If I am increasing my input value by a small amount, let us take del V. What will happen? The gate, that is a voltage between the gate and source, voltage between the gate and source, that will be decreased. Because of this, your drain current will be lower. Drain current is nothing but I equal to what, V by R. So here we are considering that V as del V. So V by R, 1 by R equal to transconductance. So we are taking that as GM. So that your drain current will be lowered by the amount GM del V. Next, because of this, your V out will be raised by the amount V equal to I into R. So I is GM del V. What about R? R equal to RD. So because of this, your output will be raised by the amount GM del V into RD. So next, what is your voltage gain? V out by V in. If you are substituting V out GM del V RD and V in equal del V, what will happen? Your gain will become GM into RD. This is your gain. And next, we are going to see what is my input impedance and what is our output impedance. Before that, here we have to maintain our M1 at saturation. In order to maintain this transistor in saturation, the one condition should be satisfied. So what is the condition is VDD minus IDRD. The voltage at this drain is VDD minus IDRD. That should be greater than VB minus VTH. This should be satisfied to maintain this M1 in the saturation region. Okay, this is what one condition here. And next, what is the input impedance and output impedance? So this is my small signal equivalent circuit of input impedance. This is the small signal equivalent circuit of output impedance. So here let us take this input impedance. Here we are giving, that is our gate is connected to, we are considering that gate is common now, so gate is connected to ground. We are giving input at source, and this is my output side. So this is the equivalent current source GMV1 and output resistance RD. So say we are giving the input, let us take that is Vx, and this is what input impedance circuit, and this is my output impedance circuit. While finding this output impedance, we are making the input voltage at source is 0. So gate already 0, gate is connected to ground and source is connected to ground. And next, this is my output side. So GMV1 resistance RD. Here we are giving small output voltage, that is voltage Vx, and the current from this source is flowing inside this, that is Ix. Here what is my input resistance Rn and what is my output resistance Rout. From this circuit we can say V1 equal to minus Vx. Okay, so from this from figure 1 we can say V1 equal to what? Minus Vx. So what is my Ix? What is the current flowing through this Vx? So that is I equal to what? V by R. That is Ix equal to minus Gm into V1. instead of this V1 we can write minus Vx, so minus into minus plus, so this will become Gm Vx. So Rn is nothing but 1 by Gm. Here Rn is nothing but 1 by Gm. So Rn is very lower value, that is Rn here is lower value. From figure 2 we can write what is our output resistance R out. So here gate voltage is 0 now, so V1 equal to 0, so Gm V1, this will become 1.6, that is this will also will become 0. On the output side we are having only RD, so R out always depends on this RD, so R out will become RD. R out is equal to RD. This is our input and output impedances. Next we are going to see if we are connecting resistance at source side, what is our circuit, how our circuit will behave, that is how what is our voltage gain, that is what we are going to see now. So this is a diagram here. This is same as previous diagram only, but the difference is here we are connecting at this source side we are connecting resistance Rs. So how this will affect your output, that is what we are going to see now. So for this here at this point we are having the input impedance 1 by Gm, and this is what the equivalent circuit of this circuit. So here V in Rs we are having, and 1 by Gm at this point we are having 1 by Gm. So this is by point Vx. This is what are the input side. Next, what is our Vx here? V equal to nothing but here this resistance divided by sum of these two resistance into the input voltage. So here V in, so Vx equal to 1 by Gm divided by 1 by Gm plus Rs into V in, that is what the formula here. And next here we are taking Gm outside, so what will happen, 1 plus Gm Rs, that Gm I am taking that into numerator side, so these two will become 1. So finally you are getting Vx equal to 1 by 1 plus Gm into Rs, Gm Rs into V. This is my Vx voltage at this point, that is Vx. Next we are going to calculate what is our gain. We already know gain is equal to V out by V in. Here I am including Vx voltage, so V out by Vx into Vx by V in. So what is Vx by V in? V out by Vx is nothing but we already found that is GMRD. GMRD. What is Vx by V in? Vx by V in equal to 1 by 1 plus GMRS. So 1 by 1 plus GMRS and into V out by Vx equal to GMRD. Here I am taking Gm outside, so this Gm and this Gm will be cancelled. Finally we are getting Rd by 1 by Gm plus Rs. This is what our gain. So here and this gain is equivalent to degenerated common source stage. This is already we discussed this one. So this is nothing but this is equivalent to degenerated common source stage. Only difference is we are having minus sign in this degenerated common source stage. Here we are having positive. So this, if you are connecting the resistance at source side, you will be getting the gain like this. This gain will equal to, this is equivalent to degenerated common source stage. Only difference is negative sign. And this is whatever output resistance 1 plus Gm R naught into Rs plus R naught. This is what about behavior of common gate stage with finite source resistance. And next we are going to see common gate stage with biasing. So common gate stage with biasing, this is whatever circuit. Here we are connecting at the gate side we are connecting R1, R2, but these are biasing resistors R3 at source side and coupling capacitors C1. This is your biasing circuit. So here at this point X your resistance 1 by Gm we are already having input resistance. So at this point your resistance will become that is parallel, your 1 by Gm input resistance is parallel with R3. So how to find this voltage gain? V out by Vn equal to, again I am including Vx here, so V out by Vx into Vx by Vn. So we already know V out by Vx equal to GMRD. What is my Vx by Vn? So here extra we are having one R3 that is parallel with 1 by Gm now. So we can rewrite this Vx Vn equation. So here we are having only 1 by Gm, but in this circuit we are having extra R3 that is parallel with 1 by Gm. So what will happen, instead of writing 1 by Gm, here we have to include R3. So the R3 parallel with 1 by Gm divided by R3 here. Instead of 1 by Gm, write 1 R3 parallel with 1 by Gm divided by R3 parallel with 1 by Gm plus Rs into V. That is the only change here. So instead of 1 by Gm, include parallel R3 also here. So this is what your gain of this biasing circuit. So this is whatever common gates stage. Thank you all.